Breaking barriers, Rosatom's groundbreaking plasma rocket technology set to slash Mars journey to just 1 to 2 months. Date, February 10, 2025. Rosatom, the state nuclear agency of Russia, has made headlines with the announcement of a revolutionary laboratory prototype of a plasma electric rocket engine which has the potential to cut the travel time to Mars to just 1 to 2 months. This cutting-edge technology utilizes a magnetic plasma accelerator, marking a significant shift from the conventional chemical rocket engines that have dominated space travel to date. Key features of the plasma rocket engine. 1. Engine specifications. The plasma rocket engine operates in a pulse periodic mode, achieving an average power output of approximately 300 kilowatts. It can accelerate charged particles, specifically electrons and protons, to speeds of up to 100 kilometers per second, about 62 miles per second. This speed far exceeds the maximum velocities of traditional engines, which are limited to approximately 4.5 kilometers per second due to combustion constraints. 2. Thrust in design. The engine generates a thrust of approximately 6 newtons. It utilizes high voltage across 2 electrodes to create a magnetic field that propels charged particles, generating thrust with minimal thermal stress on engine components. 3. Testing and development timeline. A specialized 14-meter-long vacuum chamber is being constructed to simulate outer space conditions for rigorous testing of the prototype. The prototype, developed at Rosatom's Troitsk Institute, will undergo extensive testing to refine its operational modes, with a flight model anticipated by 2030. 4. Journey reduction impact. Current Mars missions typically take nearly a year to complete, exposing astronauts to prolonged cosmic radiation. By reducing the journey time to just 30 to 60 days. This new technology not only enhances mission efficiency but also significantly minimizes health risks associated with long-duration space travel. Comparative insights from various sources. Common points. All sources highlight the potential for reduced travel time to Mars and emphasize the innovative nature of the plasma propulsion system compared to traditional chemical rockets. The safety and efficiency benefits due to shorter travel durations are consistently noted across reports. Differences. Some articles provide detailed technical specifications of the engine, while others focus on the broader implications for future interplanetary travel and potential applications beyond Mars. For instance, one source discusses the potential for using this technology in space tugs for cargo transport between planets. Future implications. The successful development of this plasma rocket technology could fundamentally change the landscape of space travel, making Mars more accessible and potentially opening pathways to destinations beyond the solar system. This research aligns with global efforts from various space agencies, including NASA and the European Space Agency, which are also working to enhance interplanetary travel capabilities. Summary. In summary, Rosatom's plasma rocket engine represents a significant advancement in space propulsion technology, with the promise to redefine the timelines and safety parameters of future manned missions to Mars and beyond. Continued testing and development could soon transform the ambitious dream of rapid interplanetary travel into a practical reality. Source summaries. 1. World Nuclear News. The article outlines the prototype's capabilities, emphasizing its potential to reduce travel time to Mars significantly. It describes the engine's operation and the planned testing in a specialized vacuum chamber. 2. Interesting engineering. This source focuses on the operation of the engine, its superior speed capabilities compared to traditional propulsion systems, and the implications for astronaut safety and mission efficiency. 3. Deccan Herald. The piece highlights the innovative nature of the plasma propulsion system and its potential to make interplanetary travel faster and more feasible. It discusses the preliminary design and future testing phases leading to a flight model by 2030. As space exploration continues to evolve, Rosatom's advancements in plasma rocket technology may pave the way for a new era of rapid interplanetary travel, bringing humanity closer to the stars. The development of Rosatom's plasma electric rocket engine marks a pivotal moment in the field of space propulsion technology, offering potential advancements that challenge conventional wisdom about space travel efficiency and safety. Here are some counterintuitive insights regarding this breakthrough technology. 1. Speed versus fuel. Traditional rocket engines rely heavily on fuel combustion, limiting the maximum speed of spacecraft to around 4.5 kilometers per second. In contrast, Rosatom's plasma rocket engine can accelerate particles to speeds up to 100 kilometers per second without the extensive fuel needs associated with combustion. This challenges the long-held belief that faster speeds necessitate greater fuel consumption, suggesting instead that advanced propulsion can achieve higher velocities with minimal fuel requirements. 2. Reduced journey time and health risks. The notion that space missions to Mars inherently take nearly a year, exposing astronauts to prolonged cosmic radiation, is fundamentally challenged by the plasma rocket technology. By potentially reducing travel time to just 1 to 2 months, this technology not only enhances mission efficiency but also significantly mitigates the health risks associated with long-duration spaceflight. This counterintuitive benefit highlights that faster travel can lead to safer missions, contradicting the assumption that longer missions are more manageable due to gradual acclimatization. 3. Thermal stress management. Most conventional engines generate significant thermal stress due to fuel combustion, which can lead to failures or the need for complex cooling systems. In contrast, the plasma rocket operates with significantly lower thermal stress since it does not require extensive heating to achieve thrust. This challenges the notion that high-power output systems must always manage high thermal loads, suggesting instead that innovative design can lead to efficient power conversion with less thermal management. 4. Launch methodology. The expectation that all space travel must begin with powerful chemical rocket launches is also contested. While the plasma engine will initially require traditional chemical propulsion to reach orbit, its subsequent use in space demonstrates that future missions could rely more heavily on electric propulsion systems once in orbit. This indicates a paradigm shift in how space missions can be structured, allowing for more efficient use of resources once spacecraft are free from atmospheric constraints. 5. Interplanetary travel scope. The assertion that this technology could enable access not only to Mars but potentially to locations beyond the solar system is a bold claim that challenges existing limitations of interplanetary travel. It suggests a future where the vastness of space becomes more navigable, countering the long-held belief that interstellar travel is a distant dream reserved for science fiction. 6. Testing and development timeline. The timeline for developing a flight model by 2030 may seem optimistic given the historical challenges associated with space technology development, yet this rapid pace is indicative of the accelerating innovation in propulsion systems. It challenges the typical assumption that such groundbreaking technologies require decades of refinement before they can be operational, suggesting that advancements in engineering and materials science could allow for quicker transitions from prototypes to functional systems. 7. Potential for space tugs. The application of plasma propulsion technology for space tugs and cargo transport between planets introduces a novel use case that goes beyond human exploration. This challenges the conventional view that advanced propulsion technologies are exclusively for crewed missions, indicating that they could play a crucial role in strengthening logistics and infrastructure in space, thereby enhancing the overall viability of long-term human presence beyond Earth. 8. Energy conversion efficiency. The efficiency of energy conversion in the plasma rocket, with the claim that electrical energy is nearly entirely converted into motion, defies the typical expectation that energy losses are inherent in any propulsion system. This suggests a level of efficiency that could redefine energy use in space travel, prompting a re-evaluation of how propulsion systems are designed and implemented. In conclusion, Rosatom's plasma rocket engine technology not only sets a new benchmark for speed and safety in space travel but also challenges many foundational concepts in aerospace engineering. The implications of these advancements could reshape our understanding of space exploration, making interplanetary journeys shorter, safer, and more efficient than previously imagined. The report on Rosatom's groundbreaking plasma rocket technology introduces several key points that, while highlighted, contain nuances and implications that many readers may overlook. Here are some of those important aspects and their significance. 1. Engine specifications and operational mechanism. The plasma rocket engine operates using a magnetic plasma accelerator, which is a departure from traditional chemical propulsion systems. This technology allows for the acceleration of charged particles, electrons and protons, to speeds of up to 100 kilometers per second. While the report mentions these specifications, it's essential to grasp the implications of this technological shift. Traditional chemical rockets are limited by the energy density of their fuel, which constrains their velocity. The plasma engine's ability to generate thrust without the extensive heating associated with combustion means lower thermal stress on components, potentially leading to longer-lasting engines and more reliable missions. This could revolutionize not just Mars travel but all future space missions. 2. Health and safety considerations. The reduction in travel time to Mars from nearly a year to 30 to 60 days significantly decreases the exposure of astronauts to cosmic radiation. This aspect, while mentioned, carries profound implications for human space exploration. Prolonged exposure to cosmic radiation poses serious health risks, including increased cancer risk and acute radiation syndrome. Shortening this exposure time could make manned missions to Mars feasible in the near future, addressing one of the primary concerns that current missions face. 3. Thrust capability. The reported thrust of approximately 6 newtons may seem modest compared to conventional rockets, but the key advantage lies in the engine's operational efficiency and ability to sustain thrust over long periods. This continuous thrust capability allows for smoother acceleration and deceleration phases, which is vital for deep space travel. Many readers might overlook how this gradual change in velocity reduces the physical strain on spacecraft during maneuvers, which can contribute to the integrity and longevity of missions. 4. Testing infrastructure. The construction of a 14-meter-long vacuum chamber for testing the prototype is a crucial step towards validating the engine's performance in conditions that closely mimic outer space. While the report notes this construction, the significance of such rigorous testing cannot be understated. It demonstrates a commitment to thorough scientific validation before any flight model is developed. This level of testing is essential for ensuring the safety and reliability of the technology, which is often glossed over in discussions of new propulsion systems. 5. Future implications beyond Mars. The report suggests that the technology could lead to interplanetary flights and even journeys beyond the solar system. While this is an exciting prospect, it is significant to recognize the broader implications for space exploration as a whole. Achieving faster travel times can make multiple missions to various celestial bodies more feasible, opening up possibilities for colonization, resource extraction, and a deeper understanding of our solar system. It could also facilitate international collaborations in space research, an often overlooked aspect of technological advancements in space exploration. 6. Potential economic impact. The mention of using plasma propulsion for space tugs indicates the potential for commercial applications beyond NASA missions. This technology could lead to the development of a new sector in the space industry focused on cargo transport between planets, which could revolutionize how we think about resource distribution and management in space. The economic implications of such technologies are vast, as they could lower the costs associated with space missions and stimulate growth in the commercial space sector. 7. Technological feasibility and challenges. While the report is optimistic about the potential of the plasma rocket engine, there is a notable absence of discussion on the technical challenges and uncertainties that lie ahead. For instance, the transition from a laboratory prototype to a full-fledged flight model involves extensive engineering challenges. including ensuring the reliability of the engine over long missions, managing the power supply, and mitigating potential failures in the harsh environment of space. Addressing these challenges is crucial for the technology's success and should be part of any comprehensive analysis of its prospects. 8. Comparative global efforts. The report briefly mentions that other space agencies are also working on reducing travel times to Mars. It is significant to recognize that this advancement by Rosatom positions Russia as a competitive player in the field of advanced space propulsion. The competition could lead to accelerated innovation and collaboration, ultimately benefiting global space exploration efforts. Understanding this competitive landscape is essential for framing the significance of Rosatom's development in a broader context. 9. Long-term vision for space exploration. The idea that this technology could facilitate travel beyond the solar system hints at a long-term vision for humanity's presence in space. While the immediate focus is on Mars, the implications of faster travel could lead to human exploration of exoplanets, asteroids, and potentially even interstellar missions. This perspective invites readers to think beyond current technological limitations and consider the evolution of human space exploration as a multi-generational endeavor. In summary, while the report on Rosatom's plasma rocket technology provides exciting insights into its capabilities and potential impact on Mars travel, several nuanced aspects warrant deeper consideration. From health and safety implications to the broader economic and exploratory contexts. Understanding these elements enhances the significance of the technology and its role in shaping the future of space exploration. 1. Technological innovation and specifications. The development of Rosatom's plasma electric rocket engine marks a significant leap in propulsion technology. Unlike conventional chemical rockets, which are limited by combustion speeds, the plasma engine utilizes a magnetic plasma accelerator to achieve speeds of up to 100 km per second, 62 miles per second. This capability allows for a drastic increase in average power output, approximately 300 kilowatts, and thrust around 6 newtons, which could enable interplanetary travel to Mars in just 1 to 2 months. This innovation fundamentally alters the landscape of space travel by providing a method to accelerate charged particles efficiently, which could lead to faster and safer missions. 2. Health and safety implications for astronauts. The reduction of travel time to Mars from nearly a year to approximately 30 to 60 days has profound implications for astronaut health and safety. Prolonged exposure to cosmic radiation presents significant health risks, including increased cancer risk and other radiation-related illnesses. By minimizing the duration of space travel, Rosatom's technology could significantly reduce these health hazards, making manned missions to Mars not only more feasible but also safer for astronauts. This aspect of the technology emphasizes the critical intersection of innovation and human safety in space exploration. 3. Future of interplanetary travel and beyond. The successful implementation of the plasma rocket technology could revolutionize future space missions, not only to Mars but potentially to destinations beyond the solar system. The ability to achieve higher speeds and reduce travel times opens up possibilities for more frequent and extensive exploration of other planets and celestial bodies. Furthermore, the technology may also find applications in space tugs for cargo transport between planets, enhancing the logistics of space missions and paving the way for deeper space exploration. 4. Testing and development timeline. The rigorous testing and development of this plasma rocket technology is crucial for its eventual application in space missions. The establishment of a specialized 14-meter-long vacuum chamber for simulating outer space conditions underscores the commitment to thorough research and validation of the engine's performance. The timeline anticipates a flight model ready by 2030. Which highlights the structured approach taken by Rosatom to ensure that the technology is not only innovative but also reliable and safe for practical use. This methodical progression towards deployment reflects the complexities and challenges inherent in advancing space propulsion technology. 1. Viking 1 and 2 missions 1975 to 1976. NASA's Viking program consisted of two spacecraft, Viking 1 and Viking 2, which were the first to successfully land on Mars and conduct extensive scientific experiments. Each mission took nearly 11 months to travel to Mars, showcasing the limitations of chemical propulsion systems at the time. The data gathered from these missions provided critical insights into Martian geology and atmospheric conditions, paving the way for future exploration in missions. 2. Apollo Program 1961 to 1972. NASA's Apollo program was a landmark series of missions that successfully landed humans on the Moon. The program's use of Saturn V rockets, which relied on chemical propellants, allowed astronauts to travel to the Moon in approximately 3 days. The Apollo missions demonstrated the challenges of human spaceflight and the need for advanced propulsion technologies, highlighting the potential benefits of faster travel times for future missions beyond Earth's orbit. 3. Project Orion 1946 to 1965. This U.S. project aimed to develop a spacecraft propelled by nuclear pulse propulsion, which would theoretically allow for faster interplanetary travel. The concept involved detonating nuclear bombs behind the spacecraft to provide thrust. While never realized, the project highlighted innovative ideas in propulsion technology similar to Rosatom's plasma rocket engine and emphasized the need for groundbreaking approaches to reduce travel time for manned missions to distant destinations like Mars. Future outlook: predictions for Rosatom's plasma rocket technology. The unveiling of Rosatom's groundbreaking plasma rocket technology signals a transformative era in space travel, particularly for missions to Mars and potentially beyond. As the world looks to the future of interplanetary exploration, several key predictions can be made regarding the implications and advancements stemming from this innovative propulsion system. 1. Reduced travel times. With the plasma electric rocket engine capable of cutting Mars journey times to just 1 to 2 months, we can anticipate a dramatic shift in mission planning and execution. The ability to reach Mars in such a short timeframe will likely lead to an increase in the frequency of missions, enabling more extensive exploration of the Martian surface. This accelerated timeline could also facilitate longer duration missions, as astronauts would spend less time in transit and more time conducting research and experiments on Mars. 2. Enhanced safety for astronauts. One of the most significant advantages of shorter travel times is the reduction in astronaut exposure to cosmic radiation. Current missions expose astronauts to radiation for nearly a year, raising health concerns. By minimizing this exposure, the new technology will make manned missions to Mars safer. Future missions may include robust health monitoring systems that can better manage astronaut well-being during transit, potentially paving the way for deeper space exploration. 3. Potential for long-duration missions beyond Mars. The implications of the plasma rocket technology extend beyond Mars. As the vehicle becomes capable of reaching Mars in 30 to 60 days, similar technologies could be adapted for missions to the outer planets such as Jupiter and Saturn, or even for crewed missions to the moons of these planets. This advancement could lead to the first human explorations of moons like Europa or Titan, which are believed to harbor conditions suitable for life. 4. Increased collaboration in space exploration. As Rosatom's technology matures, it is likely to attract interest from international space agencies and private space exploration companies. Collaborative efforts could emerge, sharing resources, technology, and expertise. Such partnerships may lead to the establishment of a global framework for interplanetary missions akin to the International Space Station model. 5. Impact on space cargo transport. The plasma rocket technology may also revolutionize cargo transport in space. With its capacity for rapid acceleration and deceleration, this propulsion system could be adapted for use in space tugs, facilitating the movement of cargo between planets. This capability would enable the establishment of a more sustainable and efficient logistics network in space, crucial for supporting long-term human presence on Mars and beyond. 6. Advancements in propulsion technology. The development of the plasma rocket engine is likely to spur further innovation in propulsion technology. As researchers refine the design and operational parameters of the engine, new propulsion concepts may emerge, including hybrid systems that combine plasma propulsion with other technologies. This could lead to breakthroughs in energy efficiency and thrust generation, influencing a wide range of space missions. 7. Economic and commercial opportunities. The successful implementation of this technology may give rise to a new market for space travel and exploration. Companies focused on space tourism, mining asteroids, or even colonizing other planets could emerge, leveraging the reduced travel times and enhanced safety provided by the plasma rocket. This commercial landscape may attract significant investment, driving further technological advancements and making space more accessible. 8. Public engagement and interest in space exploration. The prospect of faster journeys to Mars and beyond could rekindle public interest in space exploration. This renewed enthusiasm may lead to increased funding for space missions, educational programs, and public-private partnerships aimed at expanding human presence in space. As missions become more feasible, we may witness a cultural shift towards viewing space exploration as an attainable goal for humanity. 9. Sustainability and resource utilization. As missions to Mars and beyond become more frequent, the focus will likely shift towards sustainability in space exploration. The need for efficient resource utilization, including water, fuel, and materials, will become paramount. Technologies developed for plasma propulsion could contribute to in-situ resource utilization (ISRU) strategies, enabling astronauts to generate fuel and other essentials on Mars, thereby reducing dependency on Earth. 10. Timeline for realization. While the prototype's development is promising, the timeline for full realization and operational deployment remains critical. The completion of extensive testing and the expected readiness of a flight model by 2030 will be pivotal. Success in this phase will determine the feasibility of launching manned missions within the next decade. Conclusion. Rosatom's plasma rocket technology heralds a new era in space exploration, promising to make human travel to Mars and beyond faster, safer, and more efficient. The implications of this technology will likely reverberate through various sectors, from scientific research to commercial ventures, as humanity takes significant strides toward becoming a multiplanetary species. As we move forward, continued investment and international collaboration will be essential to fully realize the potential of this groundbreaking advancement in space propulsion.